Welcome to Jarnac Tutorial 1. Jarnac is a script-based simulation application. Biochemical models are described by specifying reaction schemes in the form of text. In the following tutorials, we repeat the earlier tutorials based on JDesigner, this time in terms of Jarnac. Let us begin by building a simple network. This network will comprise of 4 molecular species and 3 reactions. Start by creating a new file. Then, select the lower window. First, we will define our network object. The pathway, P here, is a variable that represents the model we are creating. Next, we will declare our species, variable node 0, node 1, node 2, and node 3. Then, we will define each reaction in rate law. The first reaction, J0, will be a simple uni-uni reaction between node 0 and node 1, with rate law K0 times node 0. The other 2 reactions will follow this pattern. And then finally write end. We will then initialize each of the variables, starting with the concentrations of each node. Node 1 will be set to 10 units, while all 3 of the other nodes will be set to 0. Next, we will set the initial concentrations for our rate constants. Set K0 to 0.6, K1 to 1.0, and K2 to 0.15. To run a time course simulation, we will first define variables for the start and end times, as well as the number of data points we wish to collect. We will set time start to 0, time end to 10, and num data points to 100. To perform the simulation, we create a matrix using the method sim.eval and pass it to the graph function. Then, click on the Run button to have the graph be displayed. The graph can be copied by clicking on the Copy to Clipboard button. You can edit your axes and other graph properties using the Edit Chart button. To obtain raw data, simply add the line print_m to your script, which displays the matrix created in tabular format. Click Run to see these results. We are now going to make a change to the model by setting different rate laws for the 3 reactions. In the earlier version, all the rate laws were simple, irreversible mass action rate laws. For many models, this may not be realistic. Instead, we will employ in the next version reversible Michaelis-Menten rate laws. We have the option of typing in our own free format rate laws, or we can take advantage of Jarnac's built-in rate laws. The built-in function UUR evaluates a single substrate reversible Michaelis-Menten model. Now, we will redefine our reactions by changing each of the reaction rate laws to be uni-uni reversible Michaelis-Menten. After changing the reaction rate laws, we will initialize our parameters and variables. Node 0 will be set to 10 units, while all others will be set to 0. The values for the reaction parameters can be seen on the screen. To create a graph, we will copy our simulation data from the previous example and click Run. We will now learn to set boundary conditions and calculate the steady state. To set node 0 and node 3 as boundary species, we declare them as ext variables and put a $sign in front of the species in the reaction declaration. Then, remove nodes 0 and 3 from the time course simulation data. Then, run the script to see the graph appearing on screen. Notice that this time the system approaches a steady state. To calculate the steady state, we remove our time course simulation code and instead run a steady state simulation using the ss.eval method. In our code, we run the steady state simulation and then print the steady state concentrations for node 1 and node 2. Running the script, we see the steady state concentration appearing in the console windows. Another way to print this information is to type p.fs in the console window to show the nodes, and type p.sv to show their concentrations. This concludes Jarnac Tutorial 1. In Tutorial 2, we will introduce the notion of a pathway flux.